Good evening, everyone. I welcome you all to the week 2 live interactive session on applied thermodynamics for engineers. My name is Abhishek. I am a PMR research scholar in the Department of Mechanical Engineering, IIT Guwahati. So, if you have any of your doubts in any of the lectures and if you want to interact with me, you can directly write a mail in my Gmail ID. This is my Gmail ID. You can write a mail and I will be more than happy to answer you. Then other things that if you are missing some lectures or you want to see the live lectures again, you can directly see them on this YouTube channel. So let's start for this week. So in this week, we have covered lecture number 5, 6, and 7, and in which we'll be covering the different types of Maxwell relations and also other types of equations like Clausius-Clapeyron equations or even Joule-Thomson coefficient. Now, before that, we have already covered the three basic laws of thermodynamics, and that is zeroth law of thermodynamics, first law of thermodynamics, and the second law of thermodynamics. Now, in zeroth law of thermodynamics, we learned how to measure the temperature. Now, once we learn how to measure the temperature, we can use it to calculate different properties like energy and work interactions, which is defined by the first law of thermodynamics. Now, after calculating all this, we want to find out the efficiency, and the efficiency we can compare it with the maximum efficiency, that is the Carnot efficiency, which is possible between any two temperature limits. Whenever there is there is an energy interactions, we will assume that it is interacting between two different temperature limits, and between two different temperature limits, there can exist a heat engine which will be having efficiency, and that will be the maximum efficiency, and it is called Carnot efficiency. Now, second law of thermodynamics tells us the direction in which the process takes place. So this is the second law of thermodynamics, this is the first law of thermodynamics, and this is the zeroth law of thermodynamics. Okay. Now, once all these things are done, but in real life scenarios, whenever we are talking about any chemical factory or even any thermal industries, there will always be dealing with a different thermodynamic potential, which are like the internal energy. This is the internal energy. This is the enthalpy. And I hope you know all the definitions of all this because this has been covered in the lectures. This is the Gibbs free energy and the Helmholtz free energy. Okay. Now we can calculate the interrelationship between this by using this square, like H is equal to U plus PV. And this has been very widely covered in the lectures. Okay. F is equal to U minus TS, like this. Okay. Now, then came the Maxwell relation. Now, why the invention of Maxwell relation took place is that whenever we are dealing with any of these thermodynamic potential, we cannot measure them directly in real life because either we can measure the temperature, pressure, or specific volume, which are like measurable characteristics. Like for temperature, we can use thermocouple. For pressure, we can use pressure transducers or different types of pressure measuring instrument like pressure gauges. And specific volume, we can calculate by the mass flow rate or even the density. Okay, but other than that, we cannot measure directly the internal energy or enthalpy or Gibbs free energy. Okay, so in that case, we wanted to interrelate this thermodynamics potential with the Maxwell relations. Now, for that, we found out Maxwell relation, which tells us the relation between the thermodynamics potential and pressure, temperature, specific volume, and maybe entropy. Okay. So based on that, these are the four relations that were derived in the Maxwell relations, which we are talking about is we can find out through this to easily remember these four relations. We can take help of this square, and this has been very beautifully covered by the instructor in the lectures. So this is a mnemonics which has already been told, which is a good physicist have studied under very fine teachers. Now, based on that, we can derive all these relations from this square. For example, like the first dt by dv at constant entropy. So, for example, dt by dv, we go like this. This is dt by dv. So, dt by dv at constant entropy, and that constant will be the diagonally opposite. Dt by dv at constant entropy is equal to same at the adjacent, we'll see dp by ds, and which is the diagonally opposite of p, it's v at constant specific volume or volume. And but the only thing that we have to remember is whenever we are relating interrelating between two vertical properties, then we have to add a negative sign. Okay, so these using this square, you can easily find out all the relevant Maxwell relations. Okay, after that we also derived the relation between the du, the internal energy, and the enthalpy, specific enthalpy. So these are the relations that were developed using the Maxwell relations and few other derivations. And I would request you to go through the lectures because this has been derived very comprehensively in the lectures. So you can remember this remember these expressions, and these will be very handy whenever we are solving any numericals. So based on that, try to remember these two formulas, in which we are interconnecting the internal energy with the measurable properties like temperature and pressure and specific volume. Similarly, here the enthalpy is also connected with the specific volume, temperature, and pressure. Similarly, for entropy and specific heat also, we derived the formulas, and these formulas can be noted down as shown here. So I would request you to, again, I would request you to remember all these formulas. And the derivation can be found out in the lectures. Okay. These are the two relations for the entropy. We'll be also solving few numericals, and that will be helpful while when we are solving the numericals. Okay. Now, this relation is also named as Mayer's relations. Even this relation was also derived in the lectures. You can go through them. And a few other things that were known from this relation because were we arranged few things, and we could find out that Cp minus Cv is specific volume temperature times the beta square by alpha. What is beta? Is the volume expansion or expansivity. Okay, and alpha is the isothermal compressibility. Okay. Now beta is volume expansivity, dou V by dou T at constant pressure 1 by V specific volume. This is beta, and alpha is isothermal expansion. So dV by isothermal compressibility, sorry, dV by dP at constant temperature. And we know that there is a opposite sign for the increase of volume and pressure. Like for example, when the pressure increases, volume will reduce. So we have added a minus sign and we'll divide by 1 by V. So this is alpha. Now we have derived this equation from this expression from expression number 5. Okay. Now few of the things that can be drawn from this is that if you see closely, look at this, specific volume is always positive. Temperature is absolute temperature, so also, this will also be positive, absolute temperature. This is also positive. Beta, this is the volume expansivity. if you see this expression like dV by dt, whenever there will be increase in the temperature, there will be mostly increase in the specific volume. Only the case of water in which we will be increasing the temperature means there will be reduction in the specific volume. So in only, but if that is also the case, we have seen that it has been written as beta square. So the beta square is positive. Then comes alpha. Alpha is a positive quantity. So overall, Cp minus Cv is a positive quantity. That means Cp will always be greater than equal to Cv. The at most likely the most limiting case will be whenever Cp equal to Cv. Cp, only this case is possible. Cp can be greater than Cv or Cp can be equal to Cv at least. It can never be less than Cv. So this is one of the things that was derived. And also for incompressible systems, for simple incompressible systems, like for solids, Cp will be equal to Cv. And another case for Cp is equal to Cv is when the absolute temperature is 0. Then only Cp can equal to be Cv. Of course, this is a hypothetical case whenever the absolute temperature is 0. Okay, because we have to go till minus 273.15 Celsius. Okay. Now for lecture 7, we introduced Joule-Thomson coefficient and the Clapeyron equation. So what is Joule-Thomson coefficient? So a very simple experiment was done. For example, some gas is flowing through this, and there is a small constriction. This. Okay. Now, whenever this constriction is opened slightly, there will be a process developed which is called throttling. Okay. Now, this throttling process is highly irreversible, and here we'll be finding out that enthalpy H1. For example, this is the section 1 and this is the section 2. H1 is equal to H2. This is the case for from this only we'll derive the Joule-Thomson coefficient. Okay, this is isenthalpy process as enthalpy stays constant. Okay. Now we'll make this 0. Cp dt plus V minus T dou V by dou T. Okay. Now if you take the other side, minus Cp dou T is equal to V minus, sorry about this, V minus T dou V by dou T, constant pressure, so dou P. Now dou T by dou P you can write as at constant enthalpy is equal to 1 by Cp T dou V by dou T at constant pressure minus this. Okay, so this is called the Joule-Thomson coefficient. This is nothing but the slope of the Tp curve. Okay, when T is the y-axis and P is the x-axis, and when we will draw the series of isenthalpic process, for example, something like this. Like this is H1, H2, H3, and H4. Okay. Now, if you see, whenever we are decreasing the pressure, temperature is increasing. Let us say this is 0.1 and we are going till 0.2. Okay, so if you see, we are reducing the pressure means temperature is increasing. Okay, you can see that. So this is P1, this is P2, this is T1, this is T2. As we are going from P1 to P2, the temperature is increasing from T1 to T2. But how long does this takes place? This takes place till this point. This is called point of inflection, wherever the slope, the value of the direction of the slope is changing. Okay, this is the point of inflection where the slope is zero. Slope is zero. Okay, or mu j_t is zero. And whenever we connect all these lines together, this the maximum inversion temperature will be here whenever the pressure is zero. Maximum inversion temperature. Now, whenever we are, and in this part, we'll be finding only heating will be taking place. And this dotted line divides this whole curve into two parts. One is heating, one is cooling. Okay. So for any gas to be used as a refrigerant, it should give cooling effect. So that means it has to operate between this from below the maximum inversion temperature, and whenever mu j_t means mu1 minus mu2, let us say like that, is positive or negative? Is positive, is greater than 0. Then only T1 minus T2 is 0. Okay, that means T2 is reducing. Okay. This is negative, this is positive. Okay. Now, then came the Clapeyron equation. This equation is used generally to calculate the enthalpy or even the specific volume in a phase change process. And this is the overall formula looks like this. dP by dt is equal to H12 T sat by V12, where V12 and H12 will be telling us the enthalpy change and the specific volume change during the phase change. Okay. Now, another case is for approximation. We can think that whenever there is a conversion between a liquid vapor conversion, we can assume that vapor is behaving almost equal to a ideal gas. In that case, V12 is only V2. Okay, let us say V1 is the liquid, 2 is the vapor. So specific volume of vapor is much higher than the liquid when at low pressure. Okay. Now in that case, V12 is equal to V2, and this can be taken from the RT saturation by P saturation. Just the ideal gas equation. And when you substitute that, so dP by dt, the saturated state, is equal to H12 P saturation by T saturation square R. Okay, this is the one Clapeyron equation, and you can also integrate that by bringing P saturation to this side by P sat is equal to del T H12 by R T square. And whenever you will integrate, you will find that it is ln P2 by P1 Of course, this is saturation, two saturated states is equal to H1 by R 1 by, sorry, there is 1 by T1 minus T2. Okay. So these are all the things that were covered in this this lecture 5, 6, and 7. I have just given it in summary. For better understanding, you can always refer to the lectures, and very comprehensively it has been covered. Now coming to the numericals, we'll be solving few numericals and even some multiple choice questions based on this week's lectures. And we'll also at the end, I will give two questions which will be on real life based, like when for an industrial case, if you are dealing with any calculation for industries, how to calculate some properties in an industry, we'll also be dealing with that. Okay. So first, let's start with the question number 1. So isothermal compressibility is defined as, this I just covered. I'm giving you 2 minutes. Think about it. We have just covered. There are two properties like alpha and beta. You tell me which one is alpha and which one is beta. Alpha is what? What is beta? Beta is volume expansivity. This is isothermal compressibility. Okay. Now, what is isothermal compression? First of all, how to remember all this? I know you might be facing problems while remembering these differential equations. So try to be going to into the basics. So there are two words. One is isothermal, one is compressibility. So what does isothermal mean? That means temperature will be constant. So in all the cases, temperature is constant. Okay. Now then comes the compressibility. What is the compression? Compression means volume will reduce, pressure will increase. Okay. So it will be something like dV by dP. Okay. At constant temperature. Now thing comes, always remember both alpha and beta are positive quantities. Okay. Or mostly they are positive quantities. So you know that pressure's direction and volume's direction are opposite to each other. So we have to add a minus sign. And in both the cases, there is a reciprocal of specific volume. Okay. So this is isothermal compressibility. So which option is correct? Yeah, absolutely right. It is option D. Now coming to question number 2, for a particular substance, it represents isothermal compressibility and represents volume expansivity. Of course, if this is just some miss in type, if alpha represents the isothermal compressibility and beta represents volume expansivity, then among the following relation, which one is true? Try to find out. I'm giving you 2 minutes. First write what is alpha, what is beta, then you will be easily able to find out. So first of all, write what is beta. Beta is volume expansivity. Similarly, dV by dt at constant pressure 1 by V. Okay, this is the volume expansivity. And what is isothermal compressibility? That is del V by okay. Now just take the reciprocal of both of this. Beta by alpha is equal to 1 by dou V by dou T, dou V by dou T at constant pressure is equal to minus VV. Okay, so this one will cancel, minus dou V by dou T by dou P by at constant pressure is equal to dou V by dou P at constant T. So how to reduce that from to this, a single equation? We'll use a cyclic property. Okay. What is cyclic property? We'll write dP by dV, dou V by dou P by dou V at constant temperature into dou V by dou T at constant pressure is equal to dou T by dou P at constant volume is equal to -1. This is cyclic relation. From here, what we want? We want dou V by dou P, which is this one. If you take it to the other side, just multiply both the side by inverse of this. Dou P by dou V inverse -1. Dou P by dou V at constant T, equal to dou V by dou T at constant P, dou T by T is equal to dou V by dou P at constant T. So this will this and this will cancel out. So this is dou V by dou T at constant P is equal to dou T by dou P constant V is equal to dou V by dou P. Whenever you will put this in here, so which one will get cancelled out? Of course, this one will cancel out. So it is 1 by dou T by dou P at constant the volume, specific volume. So it is minus, okay, minus, okay, one minus sign is already there. Okay, so minus minus will become plus. This dou P by dou T at constant specific volume is equal to beta by alpha. So this one will be the answer. Okay, now we'll move ahead. Now derive a relation for the internal energy change as a gas that obeys van der Waals equation of state. Assume that in the range of the interest, CV varies according to the, so CV is equal to C1 plus C2 T. I think this type of questions example was already solved in the lecture during the lecture. So I am again giving you one more chance to solve it. Derive a relation for the internal energy change as a gas that obeys van der Waals equation of state. So what is van der Waals equation of state? P plus A by V square, V minus V is equal to RT. This is of course specific volume. Okay. Now we have to find out what is the change in the internal energy. Find out. Just giving you one more 2 minutes. Okay. So let's start. First of all, this question, write what is du. Du is equal to Cv dt plus T into dou P by dou T, the dou P by dou T at constant specific volume minus P into dV. So always try to remember these formulas. That will be very handy. So from here, one is Cv dt. Okay. In case of Cv dt, you will write C1 plus C2 T dt. So I will make some space T to P by dou P at constant volume P is equal to dV. Now just tell me what is dou P by dou T from this equation. So you will take constant as specific volume. So it is P plus Ky V square equal to RT by P minus V. Now if you differentiate dP or dou P by dou T at constant specific volume, it will be R by P minus T. So C1 plus C2T dou T plus, so D, this one is R by V minus B. So it is RT by V minus B minus P. Now what is RT by V minus B minus P? So this is A by V square. So C1 plus C2 T dt plus A by V square 0 to dV. Now just integrate this 1 to 2, integrate 1 to 2, 1 to, okay. So it will be U2 minus U1 is equal to C1 T2 minus T1 plus C2 square by, sorry, C2 by 2 is equal to T1, T2 square minus 1, T2 square minus T1 square plus A minus will go outside, then it will be 1 minus. So what is minus 1 V2? V1 by V2 will be minus. Okay, so this is what is expected from you. Okay. Now coming to the next question, a particular gas substance allows the relation P minus A plus A by V square V minus B is equal to RT. Using the Maxwell relation, find ds by dou S by dou B at constant T. Okay. Oh, okay, just to correct myself, so it is P minus. So here already there will be a minus, so that will become plus. Okay. So you tell me dou S by dou V at constant is equal to how much? Think about it. I'm giving you 2 minutes. Yeah,
According to the Maxwell's equation, dou S
yeah,
by dou V, temperature equal to constant, which is equal to dou P by dou T, volume equal to constant.
yeah, correct.
Uh, yes, sir. And then here P, which is equal to RT divided by V minus V plus A
Okay,
by V square.
okay,
Uh, and then we need to differentiate that pressure with respect to temperature,
okay,
maintaining volume as constant. Dou P
okay.
by dou T when volume equal to constant.
So what you are getting? Try to
I
calculate.
tried, sir. I'm getting R divided by volume minus B, that
Yeah,
constant. R first substitution.
okay, okay. Let's see. So for that, we'll again use that where so it is this is studied under very fine features. So what is dou S by dou V? From here, we'll go from here to here. Dou S by dou V at constant T is equal to dou P by dou T at constant volume. So from here, you have to calculate P minus A by V square is equal to RT by V minus V. So V is constant. Treat that as constant. So dou P by dou T at constant volume is equal to R by V minus P. Okay. So that is what is the answer. Okay. We'll go ahead. Tell me this one. Joule-Thomson coefficient for an ideal gas is. What is the Joule-Thomson coefficient for an ideal gas?
That is a zero, sir. Zero.
Yeah, 0. Yeah, we know that it is 0 because it is an isenthalpic process. H1 is equal to H2. So CpT1 is equal to CpT2. So T1 is equal to T2. You can directly derive from this, or we already have mu J T. What is mu J T? It is V minus dou T, sorry, dou V by dou P at constant temperature, I think. Yeah. So dou V by dou, sorry. So I will say dou JT is equal to specific volume minus is equal to dou V by dou T at pressure, constant pressure. I think this is the one by Cp, 1 by Cp. So if you also put this one dou V by dou T at constant pressure for an ideal gas, it is PV, P is equal to PV is equal to RT. So P is constant, so treat it as constant. Take P to the other side. So dou V by dou T, dou V by dou T at constant P is equal to R by P. R by P. So R by P into T is RT by P, which is V. So VV will cancel. So mu JT you will get 0 for a ideal gas. Next question. A substance can be used as a refrigerant when? This one we have already discussed. I hope you can answer this question.
Sir, the temperature is lesser than the maximum inversion temperature.
Okay.
By the meantime, mu J value, Joule-Thomson coefficient must be positive, sir. So if
Yeah.
it is negative in the sense, it indicates the heating process.
Correct.
Less than 0 means greater than 0 means positive.
Okay.
It is advisable for a refrigerant, sir.
Yeah, perfectly. You are right. So just remember this curve. These are all isenthalpic curves. Whenever we'll be reducing the pressure, the temperature will be increasing, but this will take place only to the where the mu j is 0. Mu j t is 0. Okay. Mu j t is 0. So this side will be having slope is negative. And so this will be the heating position. And this is mu j t is negative, sorry, positive. The slope is positive here. You can find out from here. The slope is positive. So this is a cooling. So a substance can be used as a refrigerant when its temperature is lesser than, yeah, and of course the temperature should be lesser than the maximum inversion temperature. So let us say this is the maximum inversion temperature where this curve joins here. Okay. Joins to the y-axis. That is the maximum inversion temperature. Above this, whatever you do, whether when you reduce the pressure, there will always be increase in temperature. So it cannot be used as a refrigerant above maximum inversion temperature. So it has to be below the maximum inversion temperature. So correct answer is C. Tell me this one. Among the following, which conclusions can be drawn from the Mayer's relation? I have already discussed this one. So try to answer this question.
Sir, option B, sir.
Option, which one?
Option D, sir, because the CP value is always greater than CV. Isobaric specific heat is always greater than isochoric specific heat.
Okay.
Then difference between isobaric and isochoric specific heats vanishes at absolute zero temperature.
Okay.
That is also true. And then both specific heats are identical for a purely incompressible substance like water.
Yeah.
So that's why it is applicable. All points are what applicable. All
Yeah.
of the above.
Yeah, perfectly. You are right. So it is Cp minus Cv is we know this is the Mayer's relation where it is specific volume temperature beta square by alpha. So from this we have known that it is this quantity is always a positive quantity. Always a positive quantity. That means Cp will always be greater than Cv. Cp will be always be greater than Cv. At minimum, it can be equal. So what are the cases when it is equal? One is absolute zero temperature. And this next case is for purely incompressible substance. Okay. So these are the two cases where Cp is equal to Cv. So all the out of this A, B, C are correct. So D. Now this is a numerical question. A fixed quantity of helium at 100 kilopascal, 293 Kelvin is taken to 600 kilopascal, 573 Kelvin during a particular process. Helium follows the relation P into V minus V is equal to RT. If for helium Cp is equal to this much and R is equal to this much, then the change in the specific entropy during the process is correct to 1 decimal place. Okay. So try to solve this question. I'm waiting for you. So first of all, write two state. What are the state point? State 1, state 2, and then solve this question.
Sir, my doubt is here entropy is the function of temperature and pressure.
Okay.
We have already derived equations. Entropy is a function of temperature, pressure, volume, like this.
Okay.
So by that time, it is applicable for ideal gas. So here, gas obeys P into V minus B equal to RT.
Okay.
So shall I use the same formula, sir? Del S equal to Cp ln of T2 by T1 minus R ln of P2 by P1. Whether it
Okay.
is applicable, sir?
No, it is not applicable, but you will find that we have before this few slides, I have written these formulas like ds is equal to two types of ds relationship. I have already said one is this and one is this. If you derive also, you will get the same relation, but don't directly use the equation that you said. That is all obviously for the ideal gas. But whenever you will use this formula, you will find that you will get lastly to that formula where is Cp ln T2 by T1 minus R ln P2 by P1. You will finally get that, but that is only possible because this is the equation. The van der Waals equation is given like this for question number 8. If, for example, some other PVT relationship is coming, then it is very difficult for you. So always try to remember the generalized equation, the generalized ds equation having
Okay, sir.
Cp. Yeah. I'm just writing it for you. Cp by T. Okay. So V by T. Sorry, I think this is to P. So V by to P.
That dou V by dou T, when pressure equal to constant, that is equal to capital R by P. Gas constant divided by pressure. So in this case only the same formula is what again coming.
Correct.
As you said
Correct.
earlier, I noted down, sir. So always I will use this formula and
Yeah.
integrate the
See,
things and get the answer, sir.
yeah, whenever you are solving any entropy questions, see, this question only comes because we are now dealing with these thermodynamic relations. Okay. But for example, the same question would have been asked in an entropy chapter wherever it is telling air. So we are treating air as an ideal gas and we are solving the directly using that formula. So be very careful whenever it says that it follows the relation. So be very careful there and use this equation there. Okay.
Okay, sir. Okay, sir. Substituted all those values, sir. Finally, I got the answer. Change in specific entropy. It is around minus 238.6 joule per kilogram Kelvin. I'm getting.
Okay, we'll see. We'll see. We'll just allow others to solve also. So yeah, so it will be this equation is given. This is equation of state for this helium gas. P into V minus B is equal to RT. So V minus B is equal to RT by P. So dou V by dou T at constant P. We are getting R by P. Okay. So when you put in this equation, you will get Cp ln T2 by T1. This one is very clear. Then dou V by dou T will put R by P. And when we'll integrate with dou P, it is minus R ln P2 by P1, which is the equation for an ideal gas. Okay. So now we'll just put the formula. So of course, try to see the unit in which it is asking. So we have not been given the how much mass of helium is being is undergoing this process. So that is why specific entropy it is asking. So delta S specific entropy is equal to Cp ln T2 by T1 minus R ln P2 by P1. So Cp is 5.1926 into 10 to the power 3 to ln T2 by T1. So T2 is 573 Kelvin by 293 Kelvin minus R. What is R? Is 2.0769 into 10 to the power 3 into ln P2 by P1. That is 600 by 100. That is ln 6. Okay. Now try to calculate this one. What is the answer? I will also calculate. So here you are getting 3482.74 minus 2.0769 into 1000 into long. This 37 to 1.30. This minus 238.56 joule per kg Kelvin. I hope you are getting this answer. Okay.
Yes, sir.
Yeah. So we'll go to the next question. Now, during a particular heating process, the temperature of air increases from 20 degrees Celsius to 300 degrees Celsius. Air is found to follow the relation P into V minus V is equal to RT. If air can be assumed to have constant value of isochoric specific heat, that is CV, is 0.731 kg kilojoule per kg Kelvin, then the change in specific internal energy during this process. Same type of question, give it a try.
Sir, the general equation change in internal energy which is equal to Cv into dt plus T into dou P by dou T volume equal to constant minus P into change in volume.
Okay.
Here it's an isochoric process. That's why
Yeah.
dV which is equal to 0. I hope so. We are going to get only du which is equal to Cv into dt alone.
Yeah.
And
See,
then we need to yes, sir.
Okay. Okay. Yeah. Tell me.
And then Cv value is given in the problem.
Okay.
Interchange in temperature is also available. 300
Okay.
to 200. Yes.
But where it is written that it is isochoric process, it is only written a heating process. Whether it is isochoric or isobaric, it is not written. The specific heat that it is giving is isochoric. Okay.
Oh, okay. Noted, sir. Noted, sir.
Okay.
Yes, sir. Yes.
But the formula that you said is right. Try to solve using that formula. Even then also you'll get the same answer.
Okay, fine, sir. Yes, sir. Here also, dou P by dou T, volume equal to constant, that is equal to capital R divided by V minus B we are getting.
Yeah.
And then minus of P. Instead
Hmm.
of P which is equal to RT by B minus B.
Yeah.
RT by B minus B minus RT by B minus B get cancelled. So
Okay.
0 into change in volume. And,
Yeah.
so that's why here we are going to get again du which is equal to CV into dt.
Okay. Yeah. That is what I was saying. So how much are you getting?
The value is change in energy 204.68, sir. That
Okay.
is in terms of yes, sir,
We'll see.
204.68.
Okay. So these are the state 1 and state 2. So we are following the PVT relation as P into V minus B is equal to RT. Okay. And we have the specific internal energy formula is CVT PT plus, tell me what is the formula? T into dou
P into
P
dou P by
dou
dou
T
T.
dou T at constant volume minus P at constant. I think V or P. It's P.
P, sir.
Yeah, it's constant volume. Okay. Now we have to calculate this one. What is dou P by dou T? When you do dou P by dou T at constant volume, it will be R by V minus B. And when we'll multiply with temperature, RT by V minus V will come as P. Okay, so it is CV dt plus RT by V minus B minus P into dou V. So this is also P. So P and P get cancelled. It is only CV dt. So here the internal energy only depends on temperature. For this case where the relation is P into V minus V is equal to RT. So it is just CV dt. So U2 minus U1 will get CV into T2 minus T1. CV, how much it is given? 0. It is asking in kilojoule per kg. Always notice all these things. 731 T2 minus T1, which is 573 minus 293. I am getting 204.68
Yes, sir.
kilojoule per kg. That is what it is asking. Okay. Then we'll move to the next question. Yeah, this is a question on Clapeyron equation. Clausius, maybe Clausius-Clapeyron also. Try to solve it. Saturation temperatures for steam at 275 kilopascal, 300 kilopascal, 325 kilopascal are this and this degree Celsius respectively. So these are all saturation pressures. These are all saturation temperature, corresponding saturation temperature. Now, if the change in the specific volume during the phase change process is 300 at 300 kilopascal is 0.60475 meter cube per kg, then the enthalpy change associated with this phase change at 300 kilopascal is how much? Okay, try to solve this question. I've already said it is based on Clapeyron equation. Try to solve this.
Yes, sir. If you are using the Clapeyron equation, dou P by dou T at a saturation point, which is equal
Okay.
to enthalpy change divided by T sat into change in specific volume.
Correct.
Here, dou P by dou T at a different state 1 and state 3 I have taken, sir. And then the change in enthalpy, we need to find T saturation. We need to find at state 2. That's why T saturation I have taken as 133.52 plus 273.
Yeah.
And here change in specific volume is given as 0.60475.
Correct.
Yes, sir. And then I tried, I multiplied that value. Finally, I got around 2161.10 kilojoule per kilogram.
Okay.
Again, I will check my
Yeah.
answers.
Yeah, sure. We'll give some more time for others to solve. Yeah. So what is the Clapeyron equation? Dou P by dou T at saturation is equal to H12 by V12 to T saturation. Okay. Now we have been given 3 points. Point 1, state point 1, state point 2, state point 3. Now if you see state point 1, what is the P saturation? It is 275 kilopascal. Now at state point 3, it is 325 kilopascal. Okay. Now this is in between both of them, it is 300 kilopascal. Okay. Now you have T saturation as well. Now, although you will be using T saturation in Kelvin, okay, always remember that. So convert this degree Celsius into Kelvin, absolute temperature scale. Okay. Now, all this is done. Dou P by dou T, we can write as dou P del P by del T saturation. This will be P3 minus P1 by T3 minus T1 is equal to H12. We have to find out V12 at the saturation point. We have to put 0.60475 into T saturation is 406.52. From here, find out H12. So P3 minus P1 is 50 kilopascal. divided by 409.242. 409.42 minus 403.58. 8.56. 8.56 into 0.60475 to 406.52. 2104. Am I right, or I'm getting to 2104.81 kilojoule per kg? How much are you getting? You are saying
2161.10, sir.
okay. Let me check again. So it is P3 minus P1. So is 36.27 minus 135.58. Okay, 0.60475 into 406.52. So it is 2. Yeah, you are right. So 2160.27. That is what I'm getting. I think it is almost close to your calculation. Kilojoule per
Sir,
kg.
having one doubt, sir.
Yeah.
Sir, instead of P3 minus P1 by T3 minus T1,
Okay.
can we substitute P2 minus P1 divided by T2 minus T1, sir? Because we know all the saturation point at
Okay.
P1 as well as P2. But
Okay.
if I am substituting, I am getting some other answer.
So that won't be the
Whether,
case. Yeah, that won't
sorry, sir.
that won't be working, because what you are doing is, see, this is a curve, is P versus T curve. Suppose the equation, the curve is like this. So whenever you are calculating, we are actually calculating the slope at this point. So you will be taking a point little bit above this and little bit little bit below this. You cannot just calculate on these two consecutive points. Okay, that is why this is dou P by dou T at saturation point. So you will be taking the pressure and the temperature's value for del P and del T around that point. For example, if it was asking 300 let us say it was asking 305 kilopascal, then would have taken a value which is little bit higher than this, little bit lower than this. Then only you can calculate the slope. Okay.
Okay, sir. Noted, sir.
I hope this is clear. Then we can move to the next question. For a van der Waals gas, the equation of state is P plus A by V square, V minus V is equal to RT. Calculate the change in the internal energy when 1 mole of the gas is expanded from 10 liters to 20 liters at 300 Kelvin, given A is equal to this much liter square atm per mole square, P is equal to this much liter per minute. Similar to the question that we solved, just a bit different. Try to solve this question. Are you solving the question?
Yes, sir. I'm trying. We need to take the general del U equation, CVDT plus temperature into dou P by dou T volume equal to constant minus P dV. Here, pressure equal to RT by V minus B minus A by V square. Then dou P by dou T at volume equal to constant, that is equal to R divided by V minus B. We need to substitute dou P by dou TV in the general change in internal energy equation.
Yeah.
If you are substituting RT by V minus B get cancelled and remaining is A by V square is available. So general formula CV into dt plus A by V square dV. So
Okay.
if you are differentiating, here CV value is not available here. How to approach that?
C value is not available. Okay. Then just take it for as air. Take it as 1.005.
Okay, sir.
So yeah, so the generalized equation for internal energy is del U is equal to CV dt plus T dou P by dou T at constant volume minus P into dou V. So the van der Waals equation is P plus A by V square by into V minus V is equal to RP. So if you go for dou P by dou T at constant volume, it will be R by V minus B. Okay. Now it is R by V minus B, and when we'll multiply with RT by V minus B, it is nothing but CV dt plus P plus A by V square minus P to V. Now CV dt plus A by V square to V. Now integrate U2 minus E1, which is also equal to del U, is equal to CV T2 minus T1 plus AY 1 by V2 minus 1 by V1. I think there will be a minus sign here. Minus, this will be plus. That is what you will be getting, 1.005. So T2, oh, temperature change is also not given. Okay, temperature change you can calculate from the equation itself, P plus A by V square, V minus B is equal to RT. Okay, now you have everything. Just substitute the values of 10 liter and 20 liter, take it in meter cube, of course. Otherwise, no need, because A and B are also given in liter per mole. Just change the value of RT. So you will find T2 from there. And that T2 you will substitute here. You'll get the value. A by, this is 1 minus 20 liter is given. Plus 1 by 10. Okay. Did you understand?
Yes, sir.
Yeah. Shall we move ahead? Or do you have some doubt?
Sir, here pressure value, sir. So how to calculate that T2 temperature, sir? Sorry, sir. I can't get it.
Okay.
T2 temperature.
T2 temperature, right? Okay. So pressure value is also missing. Okay, no problem. No problem. This is maybe pressure you change from P1. I think the question it is missing. So P1, let us say, is 1 atm, and P2 is what we are doing. Sorry, P1 is equal to, let us take 10 atm. P2 is equal to 1 atm. Okay. Just take that and you can do the calculation. Do you understand now? See, now you have P1, P2 value. Yeah. You got, no? I understand that maybe
it.
P1 was missing. Yeah, correct. Okay. Shall we move ahead? Okay. We'll now go to the next question. So this is a type of industrial question as you asked last class. So I have tried to include one of them. So let's solve this. A gas turbine power plant operates with an inlet air temperature of 300 Kelvin and a pressure of 100 kilopascal. The air is compressed to a 1 megapascal before entering the combustion chamber. In the combustion chamber, the temperature rises to 1500 Kelvin at a constant pressure. The high temperature air then expands in a turbine to 100 kilopascal. The isentropic efficiency of the compressor and the turbine is 85% and 90% respectively. Calculate the exergy destruction in the compressor, combustion chamber, and turbine. Assume air behaves as an ideal gas with constant specific heat and the ambient temperature is 300 Kelvin. Okay. Did you understand the question? Now, this is just like a power plant, and there you have to find out how much irreversibility it is there. Okay, exergy destruction you are finding out. The same as finally you should be able to find out T naught into delta S gen of that company. Okay, that is what they will ask you. So T naught is there. Only thing is delta S gen you have to calculate. And delta S gen, how many parts are there in that whole plant? If you see, one is compressor, air is compressed. So one is compressor. So first one is compressor. First one is compressor. Second one is combustion chamber. Third one is turbine. These three are the parts. So you have to calculate delta S gen for each of them. Entropy generation for each of them. Okay. Then you have to add them and finally multiply with the T naught. You will find out what is the irreversibility in the total gas turbine power plant. Okay. Did you understand the question?
Yes, sir.
Yeah. So try for at least 2 minutes. Then I will solve it. Because a similar question is coming next, and that will be a homework for you. You try to solve. Otherwise, next class I will give the solution for that.
Sir, first of all, I try to calculate the temperature at the exit of the compressor.
Correct.
And then combustion chamber is already given 1500, 1500.
Okay.
And
Okay.
then exit temperature from the turbine. First is what the isentropic condition as well as what the actual condition. because
Hmm.
isentropic efficiency is given here.
Correct.
Isentropic efficiency of the compressor, which is equal to isentropic work divided by ideal actual work.
Okay.
But for turbine, it is reversed. So actual work divided by isentropic work. So the first primary task is to calculate T2 by using the general relation T2 by T1 equal to P2 by P1 power gamma minus 1 by gamma.
Correct.
Then second step is calculating the T2 dash by using
Yeah.
isentropic efficiency of the compressor. And
Okay.
third step is calculating the T4 value and
Okay.
then T4 dash.
Okay.
First, this is the first step we need to do, sir.
Yeah. Absolutely right. So this type of question, whenever there is a power plant question, try to always make its graph. So TES plot will for a gas turbine power plant will be somewhat like this one and this one. Assuming it to be open cycle 1, 2, 3, 4. From 1 to 2, the compression is taking place, which is an isentropic process. If it is a reversible cycle, then 2 to 3 is a constant pressure cycle, and 3 to 4 is again an isentropic expansion. But in this question, what we are given is there isn't some isentropic, there is some irreversibility involved. So isentropic efficiency is given. So the temperature at the outlet of the compressor won't be 2, it will be 2 dash. And the temperature at the outlet of the turbine won't be 4, it will be 4 dash. Okay, the temperature at both compressor outlet and the turbine outlet will be little bit higher than when if isentropic process is followed. Okay, so taking that into scenario, T1 is given. T1 is 300 Kelvin. Calculate T2. How to calculate T2? It is T1 into pressure ratio to the power gamma minus 1 by gamma. Correct? Where did this come from? Can directly find out from PV to the power gamma is equal to constant. In place of V, you just substitute T by P gamma. So it is T2 by T1 is equal to P2 by P1. Here it will be gamma by gamma minus 1. When it will go to the other side, it will be opposite. So T1 is 300 Kelvin. And what is the pressure? From 1000 kilopascal to 1 megapascal. So this pressure is 1 megapascal. 1 megapascal is 1000. So 1000 by 100. The power gamma by gamma minus 1, assuming agar is an ideal gas, it is a diatomic gas. So gamma is equal to 0.4, sorry, 1.4. It is 0.4. Okay, is 0.4 by 1.4. Calculate how much are you getting as T2?
1118.2.
Okay, let me check. How much? 1000. I'm not getting that big value. So it is 10 to the power 0.4 divided by 1.4. It is 1.79 into 300. It is 538. I'm getting 538. Check your calculation again. Now the isentropic efficiency of the compressor is, first of all, it is reversible in pressure in powered consuming devices. The reversible work is lesser. Okay, so W reversible by W useful. So W reversible is Cp T2 dash by Cp into T2 dash minus T1 by Cp T2 minus T1. Okay. Now Cp cancels, so is equal to 0.85 is equal to T2 dash. That is what we have to find out, minus T1. T1 is 300 by T2 is 538 minus T1 is 238.26.
Sir, it's a work consumed device. That's why T2 minus T1 divided by T2 dash minus T1.
Oh, okay. Sorry. Yeah, you're absolutely right. I've done a mistake here. So it is T2 minus T1 by T2 dash minus. Absolutely. Yeah, you are right. Okay. So NC is equal to 0.85. This is 238.26 by T2 dash minus 300. So 238.26 divided by 0.85 plus 300. I'm getting 580.31. T2 dash is 580.31 Kelvin. Are you getting that value?
Yes, sir, roughly it's nearby only.
Okay. Then no problem. Yeah, there can be slight difference. Then once T2 dash is done, then we have to find out what is the entropy generation in this place. So how to calculate Sgen, delta Sgen? It is nothing but m dot S exit minus S inlet. Of course, m dot is not given, so leave it. It is just specific. Calculate the specific entropy generation. It is Sgen is equal to exit minus inlet. So it is just nothing but S2 minus S1. How to calculate S2 minus S1? Assuming that air is an ideal gas, it is the same formula that you were saying earlier. Cp ln T2 by T1 minus R ln P2 by P1. Are all the values given? This is not T2. This has to be actual exit P2 dash, but T2 won't change. P2 will be same, because if there is some if in the question it would have been mentioned that okay, after exit also the pressure is increasing or reducing, then there would be P2 dash. In this case, the pressure is assumed to be constant, so P2 dash and P2 will be same. Only T2 dash will change. Calculate what is delta Sgen for this. TP is 1.005.
Yes, sir. But at the beginning itself, T2 itself, I am getting 579.2 Kelvin, sir. T2 itself, so here 1000 divided by 100, 10 power, that value 0.4 divided by 1.4,
1.4.
and then multiplication with 300. That itself around
579. Okay. There might be some mistakes.
Okay.
Yeah.
That's all. That's all. That's all.
Yeah, that can.
That's
I'm
why
just telling the
T2 dash
process.
I'm getting. Yes, sir. T2 dash, I'm going to get it something higher than that of 580. That's all, sir.
Okay.
Sir.
Okay.
Understood,
No problem. Yeah.
Okay.
Just I'll check again. Yeah. So you are getting, I think, 579, right? It's 579 point something. Correct. But just see the process, okay?
Okay, sir. T2 dash now.
Sorry.
T2 dash around 628.
Okay. Calculate delta S.
del S change in entropy around 0.0824 kilojoule per kilogram Kelvin.
Okay. Del S for the compressor is 0.0.
0.08.
0.0, it's so less. Let me check again then. How much T2 dash are you saying?
T2 dash around the 628.47, sir.
This is 579.2. 79.2 minus 300. That will be 0.85. Plus 628.48. Yeah, correct. 0.8148 divided T2 dash T2 by T1 300 log into 1.005 is 0.28. 287 log plus 0.082, right?
Yes, sir.
0.082 kilojoule per kg Kelvin. Okay, so that is delta Sgen for the compressor. So calculate now excited destruction. I naught for just for the compressor is T naught into delta Sgen. How much are you getting? Into 300. 24.71. Correct?
Yes, sir.
Okay. So once that is done, so compressor is done. Then the comes combustion chamber. Now combustion chamber is very easy. Here constant pressure takes place. So delta Sgen will be S3 minus S2, which is a constant pressure process. So directly Cp ln T2 by T1. Sorry, T3 by T2. So T2 right here as T2 dash. So 1.005 into ln, it is 1500. How much is given? 1500 Kelvin. So 1500 divided by 600. How much? 628.48. 628.48.
0.874.
Yeah, 0.874 sorry, 0.874 kilojoule per kg Kelvin. What is I naught for the combustion chamber? 262.28. Correct? Are you getting that?
Yes, sir.
And then comes the turbine. Now, what is the turbines? First of all, same like compressor we have to do. We have T3 is equal to 1500 Kelvin. And we are expanding to how much pressure it is given? 100 kilopascal. Okay, the same as this one. So T4 is equal to 1500 divided by Rp to the power gamma minus 1 by gamma. So 1500 divided by 10 to the power. I'm getting 766, 776. Am I right?
Yes, sir. 766.9. Yes, sir. Correct, sir.
So this it is a power producing device. So reversible will be more. So it is T3 minus T4 T3 minus T4 dash is nothing but 0.9. I think 90% is given. Yeah. Calculate T4 dash. T4 dash is 849. I'm getting 849.23. Correct?
Yes, sir. 849.21. Yes, sir. Correct, sir.
So delta S gen for turbine is S4 minus S3. That is Cp ln T4 by T3 minus R ln P4 by P3. Calculate. And this is nothing but T4 dash, of course.
This is also around 0.0891.
0.9. Yeah. 0.0891 kilojoule per kg Kelvin. Now, what is the destruction, exergy destruction for the turbine into 300? It will be also somewhat around 26.73. So overall plant exergic destruction, if you'll see, you can calculate 26.73 plus 262.28 plus 24.7. This 313. Yeah. 313.71 kilojoule per kg. Okay, so this much exergy is being destroyed in this power plant. Okay, similarly, you can calculate for any power plant. If you have the data of all the temperature exit and all, you can easily calculate. And this is what is done in any industry to know where is the process. Now you tell me where is the maximum destruction taking place? Simple, it is in combustion chamber. Okay. And if just imagine if the isentropic efficiency will drop further and more further from 85% and 90%, there will be further exergy destruction. So this is all how it is done in the industry. Okay.
Okay, sir.
And another question, this also is somewhat like a steam power plant. And I think this is very easy. And I think you will be able to solve it. Just I will tell you how to solve it, and I will try. I will share the answer in the next class lecture, or I will upload this answer in that Google Drive link that you will get it. Okay. So it is saying that a steam boiler generates steam at 10 megapascal and 500 degrees Celsius from a feed water at 200 degrees Celsius. The feed water is pumped from the condenser at 50 kilopascal and 45 degrees Celsius. The boiler uses natural gas with a lower heating value of this much, which is burnt in excess air at a stoichiometric ratio of 20% excess air. The combustion efficiency is 95%, and the exhaust gases leave the boiler at 200 degrees Celsius. Determine the exergy destruction in the boiler. So of course, these are all the values are given, and you have to use steam's table for this, and only for the boiler it is asking. So you have to just find out the boiler's efficiency. Just if try to draw the Rankine cycle, HS plot mostly. Okay, I think it will be something like this. Okay. Then 1, 2, 3, 4. Then from there you can calculate. From there you can calculate this one. For only the boiler you have to calculate. Okay. Not for all this combustion chamber, natural gas and all. Only for the boiler it is asking. Try to solve this question. Otherwise, I will be sharing the answer for this in the next class, or I'll upload the solution. Okay. Same steps. Just calculate delta Sgen. It will be something like S2 minus S1, and then just multiply it with T naught. You'll get. Okay.
Okay, sir.
Yeah.
The average molar mass of 29 gram per mole
Yeah.
of from this, how to
Flue
calculate
gas.
mass of flue gas? Flue gas.
Yeah. So
Mass
see
flow
this
rate we need to
question.
calculate.
Yeah, flue gas means it is almost taking like air. Air's average molar mass is 29 gram per mole. Okay.
Okay.
So
Okay.
if the overall plant's destruction, excessive destruction you will calculate, then you will also calculate what is happening in the combustion chamber, how much of this natural gas is like 95% combustion efficiency is there. So the rest is getting wasted. There you will be getting to use the molar mass. For particularly for this question, you don't need to use. But still, I will share the whole excessive destruction of the whole plant. Okay. So try to
Okay,
solve it, give it a try, because such question will be very helpful. Okay.
sir. Thank you, sir.
So then we'll just conclude this session. So today what we have discussed is we have first summarized lecture number 5, 6, and 7. And after that, we solved the numerical based on that lecture. And to real life context, questions from to real life context we have already came across, out of which one we solved and one is given as a homework for you. And try to solve it, and we'll be discussing in the next class. So next class we'll again meet in the same time and the same link. Okay. Till then, take care.
Okay.
Bye.
Thank you. Thank you very much, sir.